Hi, my name's Alex Terenin, and today I'd like to tell you about Gaussian processes on Riemannian manifolds for robotics. This is a joint talk with Viacheslav Borovitskiy, who will be giving the second half of the talk. I will now briefly allow him to introduce himself.
Hello, my name is Viacheslav Borovitskiy, but you can call me Slavo for short. After Alex finishes, I'm going to tell you about geometry-aware Gaussian processes, how to define them, and how to use them. And now, I give the floor back to Alex.
Before telling you about Riemannian Gaussian processes for robotics, I'd first like to review Gaussian processes. A Gaussian process is a random function which can be used for learning and making decisions on basis of data. One of its key properties is its ability to produce not just a mean prediction, but also a set of error bars, which can be used to quantify uncertainty. The definition is as follows. A Gaussian process is a random function f from x to r such that for any set of evaluation locations, the value of the Gaussian process at those locations is multivariate Gaussian. As a consequence, every Gaussian process is characterized by a mean function and covariance kernel. If we evaluate the Gaussian process at a set of points, we obtain a multivariate Gaussian with covariance matrix induced by the kernel. To train a Gaussian process, we employ Bayesian learning, computing the conditional probability distribution of the function f conditioned on its value at the training locations. This is typically done using numerical methods. One of the key ways in which Gaussian processes are used is to build probabilistic decision systems such as Bayesian optimization. Here, our goal is to globally minimize an unknown function phi using as few pointwise evaluations as possible. The locations at which phi is to be evaluated are chosen one by one. This is done as follows. First, we build a Gaussian process posterior given the function values seen so far, which we view as a dataset. Then, we choose the next evaluation location x subscript n plus 1 so as to maximize a function alpha constructed from the posterior, which we call the acquisition function. A typical acquisition function is expected improvement, shown here. By virtue of incorporating uncertainty, this process automatically resolves the explore-exploit trade-off inherent in minimizing the unknown function, thereby allowing us to do so efficiently in the sense of regret. Let's walk through this process visually. Here, we evaluate the unknown function at a single point, building the Gaussian process posterior, whose error bars are shown. The acquisition function, shown in red, is maximized to obtain the next evaluation location. This process is repeated iteratively, obtaining better and better minima with less and less uncertainty as more information about the unknown function is obtained. The ability to use Gaussian processes to assess uncertainty and address efficient exploration extends to other settings as well. Here, we consider forecasting the motion of a pendulum from observed trajectories of motion, starting with a point x0. We forecast one time step ahead, producing a probability distribution for where the pendulum might be. We then propagate this uncertainty one more time step forward, forecasting two time steps ahead, and repeat this process iteratively. This gives us a probability distribution over possible trajectories of motion given the data we have seen so far. A Gaussian process used this way can be employed as a basic building block in model-based reinforcement learning, using methods such as PILCO. Here, we see an agent trained using PILCO solve the cart pull task using data exclusively gathered in the real world. Demonstrations such as these make Gaussian processes a promising tool to study for a wide variety of applications in robotics. I will now hand off to Slava, who will walk you through recent work on geometry-aware Gaussian processes.
Hello again, and let's now dig into geometry-aware Gaussian processes. In order to define a Gaussian process, we need to define a kernel. It's the main building block, like architecture for a neural network. In Euclidean case, what people usually do about defining a kernel is to take the member of the Matérn covariance family, the family of kernels, which is kind of a general purpose family. They're given by this explicit formula and parameterized by three very interpretable parameters: variance, sigma squared, length scale, kappa, and smoothness nu. When nu tends to infinity, this recovers a famous squared exponential kernel. And here we can see what these processes look like for different values of smoothness. For nu equal to 1/2, the Gaussian process turns out to be continuous but non-differentiable, and as nu gets bigger, the functions are more and more differentiable, and they're infinitely differentiable in the limit when nu tends to infinity. This is the squared exponential limiting case kernel. This is the famous kernel on its own, but we consider it as a special case of the Matérn family. So what if we want to model a function defined on a manifold? For instance, on a surface of this torus, or on the surface of this sphere. How can we define appropriate kernels in this case? How can we generalize Matérn kernels in this setting? So first idea that comes to mind is to use this definition. We can notice that the explicit formulas from the last slide depend only on the distance between a pair of points, and then substitute Euclidean distance for the geodesic distance on a manifold, which would yield for the special case of the squared exponential kernel this formula. Unfortunately, this approach doesn't work well. In fact, the following theorem can be proved, which states that if this function is positive definite for all values of kappa, then the manifold should be isometric to the Euclidean space, which many manifolds of interest are not. Can we get another generalization which is unconditionally positive definite for all values of length scale? It turns out that we can, but we need to take a different approach. So the approach we take is based on the stochastic partial differential equation characterization of Matérn kernels. As Whittle have shown in the 60s, Matérn kernels are kernels of Gaussian processes which solve these stochastic partial differential equations. And the squared exponential kernel is the kernel of a Gaussian process which solves the stochastic partial differential equation on the right. Here delta is the Laplacian and W is the rescaled white noise. This approach generalizes well to Riemannian setting because these stochastic partial differential equations can be transferred to this setting very easily and very naturally by substituting Laplacian for the Laplace-Beltrami operator and white noise to the corresponding white noise on the manifold. Unfortunately, though, this definition is implicit, so we don't get the formula to actually compute the kernel from this formula. But in the special case of compact spaces, it turns out that we can solve these equations analytically to get this formula. It expresses the kernel of interest in terms of a series which depends on lambda n fn, which are the eigenpairs of Laplace-Beltrami operator. It's the eigenpairs of Laplace-Beltrami operator are a kind of property of the manifold of interest. And in many cases, for example, for a circle, sphere, torus, these are given analytically. In other cases, especially in low dimensions, this can be approximated numerically. We can visualize and look at how these kernels look like here on this slide. So here is the visualization of Matérn kernel with smoothness 1/2. The first argument of this kernel fixed at the red point, and the second argument changes. In the middle and on the right, the magnitude of the kernel is visualized with color, and on the left it's visualized with the height of the blue line. With these explicit formulas, we can do Gaussian process modeling on all kinds of manifolds. As a toy example, I will show this regression problem on a surface of a dragon. So we can take some function defined on a surface of a dragon, sample some data from this function, and then learn a Gaussian process to interpolate this data. This will yield a posterior mean function on the surface of the dragon, posterior standard deviation function, and also this will allow us to draw samples from this posterior Gaussian process, which can be regarded as deterministic models interpolating our data. In order to discuss applications related to robotics, I will consider these two examples. First, I want to return to the pendulum dynamics that Alex has already discussed. In practice, many physical systems have state spaces which are manifolds, and the pendulum is not exception. The state space of the pendulum is the infinite cylinder, that is the product of circle and a real line, because the location of the pendulum is fixed to a certain circle, and the momentum is any number on a real line. So here on the left is the phase portrait of the dynamics of a pendulum. And with our kernels and the technique that Alex explained, we can do Gaussian process modeling to capture the behavior of the dynamical system behind this pendulum without knowing this system. Here on the right is the result of such modeling. With the blue on the right, we visualize confidence regions where the trajectories of the learned dynamical system lie. Note that we can do this modeling with Euclidean Gaussian processes in two different ways. First way is to consider a circle as a segment by cutting it in some point. This approach would usually lead to a discontinuity at the point where the circle is cut into, and would lead to worse modeling results. Another approach is to embed everything into three-dimensional, in this case, Euclidean space, and take the kernel from this Euclidean space. This is perfectly possible, and this would yield okay results. but would be less data efficient because the inductive bias that we use fits not so good to the problem that we actually have. So using the geometry-aware kernel helps improve data efficiency in learning dynamics. The second example is that parameters like orientation, that is parameterized by sphere, manipulability parameterized by positive definite matrix, and joint postures of some robot hand that may be parameterized by high-dimensional torus. And these are all manifolds, and sometimes in robotics the optimization problems over these spaces may arise. Bayesian optimization might be the tool for solving these optimization problems. And as it has been shown, it helps very much to use the geometry-aware kernels in these settings to improve the performance of Bayesian optimization. So this is pretty much it. And to finish, I would like to say that this talk is mostly based on our paper Matérn Gaussian Processes on Riemannian Manifolds from last year's NeurIPS. And I would like to take this opportunity to advertise our follow-up paper Matérn Gaussian Processes on Graphs, which features same ideas to define appropriate kernels for modeling functions on weighted undirected graphs. Now I want to thank you for your attention. Here are some references for the works I've been talking about. And as a last thing, I want to give the floor now to Andreas Othi. And one last time, say thank you and goodbye.